This video is made to demonstrate the working of a blockchain project done under the course 24 CYS 336 Blockchain Technology. So the intent behind this project is to improve auditability on recommender systems which uses ML or AI. Thus, we can increase our awareness while spending time on content which hooks us to it. This project harnesses blockchain technology to audit all the changes to the model parameters. So now to get started, this is the architectural diagram of the entire system. The model used here takes age, nationality, gender, current content preference, and consecutively it prompts the user what they might like. So now that we know what's happening, let's get the server up and running. So first we will start the HTML server page. I think you can see that I've started it at port 8080 using this password, and I'll go to 8080 and open it. As you can see, this is the page, and you can also see that my MetaMask is connected to this page. When you first open it, you will be like prompted to make a connection to it, and your password will be asked. And because I already did it, this got connected automatically. So now we get the bridge API and the server up and running as well. And that's the server running. So let's have it on at a view of this place. Also, as you have noticed, the server after the server has started running, the I've refreshed the desktop folder now. So you'll see the model and the user feedback, which is the data to train the model, are both added. So when there is no model, which is there in the destination folder, the server creates one and the data for it as well. If we try to log a transaction using the HTML page, the HTML basically logs the data which the user is sending to the blockchain so that it doesn't get changed in the server. So now I will log it using this account. And before that, as you can see, these are the details of the user, and this is the preference which the model is going to give us. It's predicting that the specific user might like food. And based on this preference, the user will have to either agree or not agree to it. If it doesn't agree, then the transaction will not be used to train the model. And if it does agree, then it will be used to train the model. So as you can see, the API has used the predict function. So it has taken the request from the HTML and it has used this model, which is there in a common folder, and it has created this suggestion. So let's say we do agree with it. As you can see, the feedback is now logged using the same API. So it logs the fact that the user does agree with the prediction, and we can use it to train the model. So now you can see that it's added to the network, and right as it got added to the network, we can also see the fact that the server captured the transaction and updated the model hash. So it will make more sense when I say it. And as you can see, this is the feedback at the 8th index because I've made some transactions before this and some few changes before this as well. It's for testing purposes. And this is the 8th transaction which I made to the same smart contract. And this is the hash of the model, basically hash of the model weights after the user data has been used to retrain the model. And this transaction ID, this is the ID which we can use to identify which is the transaction used to like update the model hash. So now you can also see that the web page offers another functionality, view updates. So if you use this, you can see all the updates which was made by the made in the chain. You can see that there were 8 users and like 8 updates. I mean, at each of the update, most of the updates were made by a single account, a few with another account, and the model hash after each of those, and the time during the the time when the update happened. Each of them, all of them are monitored. So yeah, the server senses the update to the chain, like the HTML updates the user data to the chain. The server senses it using Impura API, and if you refer to system architecture, you can see how exactly it's happening. So let's go to the smart contract and explore more of it after that. And before that, I would like to make a few transactions. I mean, make a few user interactions using different accounts. So now I'm going to make changes to I'm going to do another user interaction with a different account, as you can see here. So let this be the user input, and I'm going to submit the feedback. So the prediction, and let's say we do agree with the suggestion, and the user hash, which you see here, this is basically hash of the user data. So whenever we log something into the blockchain, it's mostly better to use a hash as it's storage efficient. And the other main reason why we're using a hash here is we don't want to log the personal information into the blockchain as well. So let's agree to this transaction. And yes, the 10th transaction, you need not think about the ninth one. So that's done as well. Now let's do another user interaction with another different account. Just this one, as you can see here. You can switch accounts by using this section. And yes, this is the prediction. And this time we will not agree with the suggestion. So the main difference is the transaction will still happen, the user data will still get updated, but this will not be used to train the model. So now I will explain the contract. So first, what we essentially have in this contract is the means to store the data. We are using a struct which is named update. So with this, we are stored within the struct, we are storing the user address, the hash of the user data, basically all the nationality, age, and everything, and the hash of the model weights and the timestamp when this happens. So we do have an only owner function. We'll get back to that. Before that, we'll talk about the submit user data function. So this function is essentially used by the HTML page. So when the user has to is going to input some data, which is going to be processed by the central server, the data first gets logged onto the blockchain using this function. So the sender of the message, basically the address of the user, and the data hash and the timestamp are all logged for in an update struct. Each of the element is a collection of all these entries, and the update count get incremented. So the change in the update count is essentially what is monitored by the server, with which the server will then call the attach model hash. So there is an only owner modifier restriction here. So only the owner of the function, the owner of this smart contract, is basically the person who's deploying this. And this contract is deployed using this address 75D. So the server also has the private key and everything of the 75D address which you're talking about. So that's why they are able to attach, use this function which is there in the network. And this function essentially notices the update count. I mean, the server notices the update count and it calls this function and it updates the model hash using it. And there is this get update function which is also used by the server and also the HTML page. This is used to like see all the entries of the update struct. So let's have a look at everything. So let's see the update count first. As you can see, 12 updates have been updated so far. And this is the 11th update. It's done by E0DFF, that account. And the 10th update, the 9th update, and so on. So this is a public function, so any user can access it. So even if the account was an user, they can call this function and access this data. So let's try accessing few of the functions directly using the IDE. So I am having 0C5 account as the logged in account right now. I'm going to, as the index is updated automatically, the index should be 12 now. I'm just going to attach a user data hash to it. For example, I'm just going to have it as this for now. And this is going to be the account who is going to send it. So when I access the 12th index, I should be able to see this. Stick that. And MetaMask transaction to make the change limit. Yes, the transaction successful. Let's get the 12th update. And yes, as you can see, the user data hash and the address, everything are updated. So now, as we can check the case where attach model hash is called using a normal user account and not the owner account, which is the 75D1. So now let's try with 06C5 and try this. So if I try to call it, I will get an error because only owner can call this. But if I am going to try it using the owner's address, I will be able to successfully call the transaction. Yes, as you can see here. And now that the transaction is over, the model was just updated as well. And yes, that's how the whole system works. So just to have a recap, this is the architectural model of the whole system. And thank you.